All right, so what is the 2's complement? All of us should have just written this on a piece of paper. Evan. Why is it you keep working your way back in the...
I've been sitting back here.
Really?
Since Haxton, almost died.
Oh, what class do you sit one row up?
350.
Oh, really?
He came back here during this one because Haxton left, so he was...
You were lonely.
Abandonment issues.
Do you? So,
Terrible.
there's... I was wondering if Fritz was getting in the way of the multi-threading here. What was happening? So, do you have an answer for me? Didn't you just write your answer on a quiz? Really? Let's look. Are you one of them that folded yours? The adding of an owl to the left of a binary number to get the 2's complement value allows us to do addition, subtraction, and even multiplication and division. No. Did you get it right, Tim?
Absolutely not.
Why? 2's complement is a form of a number that allows us to be able to use signed and unsigned numbers in math. Okay, well, I mean, that's more right than Evans. So what is the 2's complement?
Form of binary that allows for signed numbers in which the first digit is either negative or, well, it's negative. Yeah.
Okay, so for instance, if we had the 2's complement of the decimal number 10, that would be a negative 10.
Well, if you took the 2's complement of 10,
Correct, yeah, as an example. Using that as an example. So then the flip side of it, why do we need it? It allows us to do addition or subtraction through addition. It is a perk of 2's complement, right? We already know how to do addition, so rather than having to figure out how to do something new, let's just always do addition, but using the 2's complement of the secondary number to add rather than subtract. All right, so 2's complement allows us to represent signed numbers in binary. Would be maybe a short answer of that, and then if you were applying it to the idea of how does it benefit us, it would be the and this kind of goes along with what Abe asked last time, is why else would we use a 2's complement, right? All right.
You also said that it didn't have to be signed.
A 2's complement, well, the initial number doesn't have to be signed, but when you took the 2's complement of, if you took the 2's complement of an unsigned number, the assumption would be that it was positive to begin with, so you would get a negative number. So you don't have to take the 2's complement of a signed number.
So the result of converting something to a 2's complement would result in a sign.
Correct. Correct. 2's complement is a format for holding signed numbers. Okay, so there's a homework assignment that I've put up today, and I did go through and remove all the weird 2's and 10's from this one, so you won't have the same problem you had last time. The assignment is actually, as I currently have it set up, is due a week from today. Because there's a few things on the assignment that we haven't gotten to yet that we're going to be doing today and on Tuesday. So if for some reason we don't get through those things on Tuesday, I might push it back to the following Tuesday. But I figure it's enough tedious stuff that I wanted to give you plenty of time to work on the assignment. So there's 19 questions. Most of them are very similar to the questions from the last assignment where, do some math problem type thing. So if you do a couple of them a day between now and when they're due, it shouldn't be an overly, death-defying assignment.
You can get all the twos.
Huh?
You can get all the twos.
You watch. I did seriously go through and try to get all the twos.
You missed the first one.
Yeah, that's true. That is kind of embarrassing. You're right. I'm with you on this one. So, in any case, it is currently up on Angel, and you can look at it and start working on it. And I do have the current due date set up as a week from today.
And on number 13 there,
I screwed up again?
16's just for base 16.
All right. This is live editing. I didn't even look for 16, so that doesn't count. What is this, iOS 8? Is that it?
I'll let you know.
Right.
Answer by the side of age.
Answer by the side of age. This one? No, the question is asking, I don't know what the question is asking. Now I can look at what would be the best binary representation for each of the following applications. So it's giving you some examples of things that you might want to represent. So it's asking you to tell us what would it be an 8-bit signed number, that kind of stuff, the best way to represent it. It is messed up. I wonder if it's something with the recording or just a new Yosemite Safari prob. No, it's a Yosemite Safari prob. That's what the cool kids are using these days.
Will it actually have Yosemite as an option for OS instead of just mobile OSs if you submit it?
What?
Remember when you had an issue with your mobile OS and only gave desktop OSs?
Which was that for?
You had updated the iOS 8 or something. You had issues. You went to submit a bug.
Oh, that's right. That was the voice dictation. The voice dictation problem, where you would dictate something and it would not quite convert it, so you had to try to do it again. But then when it went to, so you voice dictated something, it would fail. Then you get all upset. Then you voice dictated again, and it would paste what you had previously recorded, the percent of it that it had figured out. So you wasted your breath the second time, and you only wasted half your breath the first time. But then when I went to go put that bug in when dictation first came out, for the operating system, it was a problem for it. Didn't offer any of the mobile operating systems, so whatever. Okay. So anyways, homework assignment's up. So let's go and look at, this is our two's complement stuff. Let's look at floating point representation of stuff. All right, so, as we're going through this, kind of think about this from our programming language perspective, and how floating point numbers might be represented in our programming languages behind the scenes. So binary numbers can also have decimal points, seeing that. And to show you how, we will once again begin with decimal numbers. For decimal numbers with decimal points, the standard way to represent the digits to the right of the decimal point is to continue the powers of 10 in descending order. So 10 to the negative 1 is 1/10 or 0.1. That means that the number 6.5342, that number, has 5 increments of 0.1, 3 increments of 0.01, 4 increments of 0.001, so on and so forth. Okay? So this kind of shows us this table of the breakdown here. All right, so at the 0 exponent, this is the ones place. 10 to the ones is the tens place. 10 to the twos is the hundreds. So this is to the left of the decimal point. To the right of the decimal point would be the points. Okay, makes sense? So this is just kind of telling us again how decimal math works, decimal numbers work. So we have this IEEE standard called 754. IEEE is one of the major standardizing bodies bodies for computing. We've probably heard of 802.11, A, B, G, N. What's the new one? Best Buy guys. Evan. The new Wi-Fi. 802.11 what? You have to have it.
We do.
Is it 802.11W or something?
Something like that.
Huh?
Well, we have the AC ones.
All right, AC would be new.
Yeah.
You've been working here, what is this tri-band one?
Yeah, the AC tri-band.
Yeah, that no one buys because no one uses it.
It's probably too expensive.
No, I sold one.
Well, you could use it. I mean, you could use it in your house. It's
But
backwards
I have a
compatible.
really big house.
Yeah, it's backwards compatible. Just like the early Wi-Fi routers were 802.11 A/B, and the difference is B was 11 megabit per second, A was 54 megabit per second. Oh, so why wouldn't everybody use A? Well, A was only for short range. B gave you a lot more distance. 802.11G gave you the speed of A with the distance of B. And then N gave us a lot more speed, and I'm not sure what this AC thing does, but it's more better.
Haven't you worked there longer than he had?
I sold more things than him.
That's because Evan's probably in the corner just crying. And
Step it up.
He just
last time somebody like messed with Evan, he put the guy in the hospital. I'm just saying. I'm just saying.
Plate glass and
All right, so we have this standard that talks about single precision and double precision floating point numbers. So floats, doubles in Java. Make sense? All right, so this allows us to represent more decimal places and a large number of bits in the front. The reality is Java actually implements theirs a little bit different, but for our example here, think of this as being a float and this being a double as the difference between these two standards. Okay, so they've broken this down into two sandwiches, if you will. So this is 23, 31, 32. So this is a 32-bit number, right? And this one is 52, 63, 64. This is a 64-bit number. Make sense? So in Java, a float could be implemented as a 32-bit number broken down like this, and a double could be implemented as a 64-bit number broken down like this. All right. So the important thing to get out of these slides is this breakdown. Very first bit is the sign bit. The next 8 bits is the exponent. The next 23 bits is the fraction. Before the decimal point, after the decimal point. Okay? And remember, this is binary representation for it. So in our computers, we're representing everything in binary. When we write our double in Java, we're saying 3.14, blah, blah, blah. We're writing it in decimal. So let's look at an example. So, and this example is going to correspond directly to, I think, at least 2 of the questions on the homework assignment. So we want to convert the 32-bit single precision IEEE Standard 754 number shown below into its binary equivalent. So this is a representation of a floating point number. We'll just call it a float, a Java float in our example, in binary. We want to give it its binary representation. This is an IEEE standard format. We want to give it its binary equivalent. So first we break it down into its 32-bit components. The sign bit, which was the original one, the exponent, the next 8 bits, and then the fraction, which is the next 23 bits. And let's see, did they add in the zeros here yet? So this is the next 23 bits would be It's 1, 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's our 23 bits. So this guy right here should be those 23 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Why did it leave off bits? I'm guessing they just made an error. Do we have them down here? Yeah, they have them down here. I think they just made an error right here. They forgot 3 zeros. When I say they, this came out of a book. The book that I didn't make you buy because it's just filled with errors. All right, so we should have all of our 23 bits here. So we break up our number into its parts. So a signed bit of 1, this very first guy, means that this will be a negative number. Okay, so we know at the end of the day, this is going to be, we have a formula we're going to look at down here, but we know this is going to be a negative floating point number. Then we have the exponent part of this number, 101011101. All right, so the exponent will be used to determine the power of 2, by which are this thing called the mantissa will be multiplied. That's like the base will be multiplied. To use it, we must first convert it to a decimal integer using the unsigned method. So if we have this number 101,011,01 in base 2, so that's where all those 2's came from. Copying it didn't like to take the subscripts. So this number in base 2 converts into what? This is 2 to the zeros. 0 times 2 to the 2, or 2 to the 1. Here's 2 to the 2, 2 to the 3, 2 to the 5, 2 to the 7. Add those all up, we get 128 plus 32 plus 8 plus 4 plus 1. That gets us 173. All right, so we converted this guy into his decimal equivalent, which is 173. Okay, nothing special there. That's nothing new, just took the exponent and converted it to decimal. All right, now, substituting these components into this equation, this guy, 1 point f, f being the fraction, this guy up here, times 2 to whatever our exponent was in decimal, minus a 127, should give us a binary number. So this is, we know it's negative, so that's where this says plus or minus 1. So this is negative 1 point, then our entire fraction, this guy with the extra 3 zeros on it, times 2 to the whatever our decimal equivalent was, 173 minus 127, which is a 46. So the binary version of this IEEE number is negative 1.01101101011 times 2 to the 46th power. Okay? So this is kind of the binary version of what we've seen as scientific notation. That make sense? All right. So let's say that we wanted to write some code to do this for us, to do that conversion. Okay? Because I always think writing the code to do it is the best way to learn how something works. Plus, I like to make you guys program. All right. So what we're going to do is we're going to take in, we'll just do this for, go ahead, sorry. This guy, that's part of the formula. If you look over here on the left, this is the actual formula for doing this. So it's plus or minus 1 point f, whatever f is, times 2 to the e, which is our conversion right here, minus 127. The 127 is a fixed value there. Yeah, we didn't solve for that. It's just as part of the equation. Why is it a 127? Can we go ahead?
Is it because E is an 8-bit signed number?
Yeah. this is always 8-bit, right? Actually, it would be an unsigned number, not signed. The sign we're handling through the sign bit. So E is an 8-bit unsigned number. No, wait. It's actually, what you said is right, but the reason is wrong. Because an 8-bit number is plus or minus 2 to the 7th power, which is negative 127 to positive 128. So that's where the 127 could have come from. But this is not a signed number. Because it's entirely possible for this entire number to be ones. And we would have gotten a 255 out of it, not a negative something. So we're going to say no. Where else would the 127 have come from? Did it just randomly pull that number out of the sky? Seems like it's got to be related to unsigned binary numbers, right? Negative 127 is just what, floating out there for no good reason? E is going to be a number in what range? This is where we're solving for E right here. What's the possible values E can be? Evan? No. E is unsigned. So you're close. I guess as close as Dr. Locklear says some people are during the CS get-together. It's an 8-bit unsigned number, so the range of values has to be positive, right? So lowest value is a 0, highest value is 255. Yeah, 256 unique values, 0 to 255. So E will always be a positive number between 0 and 255. Okay, that's what this guy will be. So this part of the equation here, E, will always be between 0 and 255. If we subtract, let's say we have a 0 here, and we're subtracting 127 from that, we'll get a negative 127, which is the smallest signed value we can get, correct? For an 8-bit E. When we throw the sign back into it. Sign comes back in down here. What if we had 255? 255 minus 127 is what? 128? All right. So that's 128. That's not right, is it? It just didn't sound right in my head. Okay, so now, so the biggest value this can be, so the smallest value this exponent can be is negative 127. The largest value this exponent can be is 128. Okay, so this exponent is a signed binary number. The exponent, the final exponent, is a signed binary number, not E itself. So our final exponent is a signed binary number between negative 127 and positive 128. And what does it mean, for instance, if we have negative 1 point blah, 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 times 2 to the 46th? That means we're going to move this decimal place over, and we're going to get, I think there's, what is there, 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to have 35 additional zeros on here for full precision. Full precision on that number. So if this number was a 128, we can have 128 bits following this number in this notation. That makes sense? But keep in mind, if we're going back the other direction, this part of E doesn't represent some sort of fixed number. Okay, when we store it, we have to store it as something like this. That's how we store it as a standard. So we store it as a 32-bit number, then we can calculate out to get higher precisions. Make sense? All right, so that's what the 127, that's where it came from, is to control the 8-bit signed aspect of our exponent. All right, so let's write a program that does this. We already have some parts of it. We already have a piece of code that will just take this number and convert it to its decimal equivalent, right? All right, so we're going to write, what do we want to call it? S754 2bin. That sounds all like creepy awesome. What's up?
The name is my goat burger.
S, what is it? 754 2bin. It's like a code name. Here, we'll actually take in an S754 variable. This will remind us that it's in S754 standard. All right, that's the format of this input. All right, so we'll take that number. Very first thing we're going to do is we're going to split it into its pieces. So let's go ahead and split into its pieces and display each of those pieces. Okay? And we're going to assume that our method only works for single precision. So just going off this example. Obviously, double precision is going to be the exact same thing, just we're going to have a bigger E and a bigger F. Right? No difference other than that. Same math. All right, so the very first thing is we're going to get our sign bit. Let's store it as a... Let's just store them as strings. Sign bit is the empty string concatenated with S754.char at 0, right? All right, now we need to get our E. String E is equal to what? It's the next 8 bits. So here's our single precision. We have 1 bit, so bucket 0 was our sign bit. E is the next 8 bits. So how do I get E out of this? If you're writing this code, how would we extract E? Fritz? I thought maybe there was like a balance of the force over here, and so it's leaving Evan. It's just waiting for one of these days when Evan snaps. We had a student years ago. I think he's before most of you guys were here. His name was Jared Fritch. Maybe you guys remember him? I think he left before any of you started, but. He was always just kind of a cool, calm demeanor guy, and so my goal was to get him to throw a desk. It was like the whole... Came from a bright family. His older brother went here as well. Both of them went to work in computer science at the Department of Defense. They're probably killing people and stuff.
Sounds fun.
Yeah, who knows?
It's not as much fun though when you're on a computer killing someone.
What's this?
Did you throw his desk?
Actually, one time, yes, but it was a joke. Some of you guys know Joey Welkley, right? He was always supposed to be the guy who was the enforcer with he would hit somebody with a chair. You know, that came up in one class as a joke, and at some point during his 4 years here, he did actually pick up a chair and hit somebody as a joke. But he like tried to fake it, but then dropped the chair. Totally hit him.
They probably just.
They did. Yeah, they did. So I turned a blind eye. I mean, the whole reason behind that is, as a professor, I'm not, I can verbally berate my students. But, if you start physically beating on students, then that becomes, you're crossing a line. But if you have a student who acts as the enforcer, and then you just happen to not see it, kind of like the professional wrestling referees. They always miss the cheating, right?
Yeah.
Yeah, same thing. Exact same thing. All right, so how do we get our exponent portion of our string?
You could either concatenate S74 add char add, and then just concatenate each one. That you know.
So bucket 1, bucket 2, bucket 3, bucket 4, bucket 5, bucket 6, bucket 7,
Or you could just do a
bucket 8.
flow.
Okay. Could do a for loop as well. Anything else?
Substring.
Substring. How about substring? So could we say S754 dot substring from position 1 to position, we're going to position 0 through 7, 0 to 8, so we want 9. So it'll be non-inclusive. So this will get us 1, 2, 3, 4, 5, 6, 7, and 8 for our 8 bits. Because 9 is non-inclusive. So this will get us everything from S754, starting at position 1, bucket 1, because we already used bucket 0 here, all the way up to, but not including bucket 9. So that should be our E. And then it is F, right? So then the fraction part should be what? S754 dot substring, the other version of substring, the one that just takes a starting index. We'll just start from 9 to the end. And this, of course, assumes that our string we passed in is indeed a legal S754 number. Okay? So just for right now, we'll return the empty string, so Java's happy with the return type here. And let's go ahead and just print out sign bit, E and F. And prove that we're getting the right stuff. All right, then we'll make our call to this. Class method or instance method? How do you know? Static. All right, so we call class methods using the name of the class in which the method was defined. And we're going to pass it. Oh, that's a picture.
That's the picture.
Just so we can compare our number. Well, whatever. Here, we're going to do this. I kind of lost my count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
It would work even if you didn't have 30.
Huh?
It would work even if you didn't have
Well, yeah, but it won't. I mean, we need to pass it a legal thing. It would work because this just says go from 9 to the end. But you're right. All right, so let's print out our pieces. So we should get a sign bit of a 1, a E of that 0, 1, 1, 1, 0, 1, 0, 1, and then an F of everything else. And of course we do. Oh, I'm missing a parenthesis. So there's our 1, there's our E, and there's our F. And let's just, huh?
You didn't need to print it out in main.
You're right. Yeah, you're right. This was a waste of time. I just printed out the empty string. This guy did all the printing. Maybe that's why I didn't put the closing parenthesis on there. All right, so We're getting our right values here. Sign bit E and F are all the right values. So now we got to do crap with those. So from our picture here, we've done this part. Split it up into our 3 pieces. Now we need to take E and convert it into its decimal equivalent. We already have a method. Is it still in converter? Binary to decimal. Oh, this asks for a number, right? Ooh, I don't like that. So there's the decimal equivalent of E. So here's the built-in way of converting a string representation of a binary number, unsigned, into its decimal equivalent. So I suppose you can use this moving forward in this class. All right, so we got the decimal equivalent of that. So that got this point. So we got this part done. Now we need to plug it into our formula. So plus or minus, that depends on whether or not we have a 1 or a 0 in our sign bit. A 1 means negative, a 0 means positive. So what we're going to do is we're going to have our string answer, and this guy will start off as the empty string. If sign bit dot equals a 1, answer plus equals a negative sign. Else answer plus equals a positive sign, just so we can specifically show whether it's a positive or a negative number. All right, so depending on whether or not it's a 1 or not, we will tack on to the very beginning, since it started off as the empty string, of our answer, positive or negative.
That'd be at the end.
Well, but it started off as empty string. So if I tack a minus onto that, we're going to have the string minus. And then we'll just tack the rest of it on after that.
Right, yeah, that's good.
This is the same thing as saying string answer here and just answer equals this or answer equals this. Just start it off the right way. Okay, so we can even do that like concatenate. We'll just start it with, we'll initialize it with the right sign. All right, and we know at the end we're ultimately going to return answer. So we'll go ahead and put that in. So now we've finished this part of it, whether it's positive or negative. Then we're always going to have a 1 followed by a period. So we might as well put the 1 period in here as well. And then we have a space followed by an X followed by a space followed by a 2. Well, actually, before we have that, we have our F. So we're going to need to insert F in there. So we happen to have F already, correct? So here, we'll just take whatever answer is. Now we're going to say answer plus equals F. So that tacked F on. Then we're going to tack on space times space 2, and then we'll do a little caret. Answer plus equals space times 2 caret. So now we're up to this point. And now what we need to do is we need to do whatever our decimal equivalent was minus 127. Answer plus equals, we called it dec E minus 127. And then we'll return our answer. And for this one, I do want to test it for our original value just so we can know whether we got it right. So 110101. One zero one zero one one. Zero one one zero one zero. One followed by 1 2 3 4 5 6 7 8 9 10 11 12. All right, so that should be our number. And now we'll go ahead and print what this guy returns. System.r. There we go. So it should be negative 1.01101101011 times 2 to the 46th. Negative 1.01101101011. We have times 2 to the 46th. Where did all these come from? We had them up here.
They just cut
Just
them off
'cause they
because
cut
you
them off,
just
yeah.
add in zeros with the.
We're going to have the zeros on there anyways, right? You know, we're going to have the zeros. So really, the accurate version of this would have been to show these guys on here, even though they're assumed to be on here right here. All right? Because otherwise you could have just put in 46, 35 zeros. 35 zeros after this, if you wanted to, rather than just these 12. All right, so that give us the right answer? So this whole thing was just about plugging it into a formula. So this is the formula for converting an IEEE Standard 754 number into its binary equivalent. Okay? Questions on that? All right, so you'll need that for the homework assignment. We've already done hexadecimal addition, right? We wrote a function to do that. So we went a little bit out of order. All right, so let's talk about multiplication and division. I don't think we've done this yet, right? We didn't do bit shifts. Okay. So, first of all, if we just do multiplication and division the way we think we should do multiplication and division, basically doing multiplication and division just like we do it with decimal numbers, but do it with binary, it would be incredibly time insensitive. Incredibly. Because think about it, when you do multiplication with decimal numbers, you basically have a row for every single number for the bottom of the multiplication. And then you add all those together to give you your answer. Correct? Well, do binary numbers typically have more digits in them than decimal numbers? Absolutely. So it would require a lot of memory to hold those individual pieces. I mean, imagine if we're multiplying a 32-bit number by a 32-bit number. To do that, we're going to have to hold 32 32-bit numbers, well, actually 35 32-bit numbers. The original 2, so that's 2 of them, followed by 32 temporary ones, followed by a 32-bit final answer. Inefficient, right? So 35 times 32 is 1,120 divided by 8 would be 140 bytes. 140 bytes to multiply two 32-bit numbers together. Not good. Not good. Especially when we think about all this stuff is likely happening at the assembly language level, so we're having to stuff all this stuff into like registers and things like that. Well, we don't have 32 or 35 32-bit registers on our CPUs. So it wouldn't even be a possibility to do this as fast math near the CPU. We'd have to outsource it out to cache or system RAM. Okay. So it's bad. All right. Division would be, let's just call it equally as bad. We can certainly see we're going to have to store a bunch of temporary stuff, correct? Okay. So we use something called bit shifts to accomplish this. So multiplication, division by powers of 2. And this is how it can work. So if we have the number 9, so this is the binary number 9, right? This is the ones place, 2s, 4s, 8. So this is an 8 plus a 1 is 9. And we multiply 9 by 2 to give us an 18. What did we do? We shifted every bit here to the left. So this 0 goes away, this 0 goes here, this 0 goes here, this 0 goes here, this 0 goes here, this 1 goes here, this 0 goes here, this 0 goes here, this 1 goes here, and then we get a new 0 here at the end. That make sense? And now we have the number 18. To get to 36, shift again, so on and so forth. Make sense? So a left shift is a multiplication by 2. A right shift is a multiplication by, or is a division by 2. Okay, so we can see that by going the other direction. If we have an 18 and we shift everything to the right, we're back to what we had for our 9. Okay, how can this work for multiplications that aren't powers of 2? So for example, let's go... We'll go right after this one. Ooh. So let's say that I'm taking the number 9 and I'm multiplying it by 5. Well, 9 times 5 is what? Nine times 5, 45, right? All right. 45, that's the answer we should get. How do we rate 45 in binary? So 9 is 1, 0, 0, 1, 1s, 2s, 4s. So there we go. That's the number 9. How's the number? How do we write the number 45? The number 45 is 0101? No, 45. 45 would be 32 plus not 16 plus 8. So now we're at 40. Plus 4 plus 1. Is that it? 32 plus 8 is 40, plus 4 is 44, plus 1 is 45. So we need to go from this number to this number using, and we're doing multiplication, so we're going to do left shifts. How do we do it? Because 5 is not a power of 2. What's the closest power of 2 to 5? 4. So if we left shift this guy 4 times, what do we get? And let's pad these out to bigger numbers. Let's just do this as a I want to do them as 32. All right. And then all right, so those are the 32-bit representations. So if we take this 32-bit number and we left shift it 4 times. So we need to left shift it once first. So we left shift it once, what do we get? We get that number, take away that 0, add a 0 onto the end, right? Left shift it again, we get that number. Left shift it again, we get that number. Left shift it one more time, we get that number. So we just multiplied it by 4. So this is the 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128. What place is this? Oh, is that the right number?
I thought every left shift was multiplied by
2. So how many times do we need to jump it? We need to do it twice, not 4 times. So we'll shift it once. And we'll shift it twice. 1's place, 2's place, 4's, 8's, 16's, 32's. So this is 32 plus 4, which is 36, which is 9 times 4. So we're good there, right? How do we get this guy now to look like this guy? Huh? Add a 9?
Well, the binary.
Okay. So we can go up to the largest value that we had. Okay, the largest value that we're multiplying by, that's closest, largest power of 2 value. Largest power of 2 value that's closest to the value we're multiplying by. Oh, I was thinking that was related to this phone call I was getting. Like, iPhone, stop talking. So then we're going to take this number minus that power of 2. In this case, we'll get 1. 1 times this guy is what we're adding to it. Correct? So if we take this number and we add a 9 to it, how do we add a 9 to this number? Doing our binary math. So we just add these two guys together. This is 1 plus 0 is a 1. 0 plus 0 is a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. 0 plus 0 is a 0. Now, do these guys match? So did we have to take up less space, memory-wise, to do that? Now, this left shift, we did it in multiple steps here, but this really could have happened in a single move, right? We're left shifting within a single register. All right, so let's go ahead and let's write a little function for left shifting. Static string left shift string bin. Okay, so how do we left shift bin? Somebody who usually doesn't answer. I want to know that your guys' brains are clicked on. So if I have this number right here, and I want to shift it to the left once, it should become that number, correct? So how do I turn this original number into this number? I'll give you a hint.
Could you just knock a 0 off the front and calculate one onto the end?
Okay, how do I do that?
You can make, to do it multiple times, you could use a formula.
I only need to do it once. How do I do this in one line of code? You usually answer. Is this a quiz? Man, Evan didn't even get the 2's complement right. What's going to happen with this one? One line of code. How do I left shift bin? Oh, start it off. I am going to return something. It's like the lightning round on a Wheel of Fortune. Fritz, you got this, right?
Substring 1 plus 0.
So get everything from bucket 1 to the end and concatenate on to 0. Return that. Is that left shift? What do you think, Evan? Why is he wrong? Why is this wrong? First, does he have YouTube up? What's he got? Are you lying? So you're going to tell me why this is wrong? I'll just comment this out. So, is that the answer we were expecting? So why is this wrong, Evan? I'm totally just screwing with you. I took advantage of the fact you didn't look up. I'm like saying to the rest of the class, it's totally right. Oh, man, I am going to get Evan to throw something. It's gonna be awesome. All right.
Don't be too mean to him. I got to deal with him tonight at work.
Really?
Yeah. He gets angry.
I could tell.
Especially when he has to walk the break.
He's adding my name to his list. All right, so we're going to take the substring from bucket 1 all the way to the end and then just tack an extra 0 into the end. So this is a way we can do this in one line. So that's a left shift. And just while we're at it, static string right shift. How would we shift it to the right by 1? You get one line of code.
It's the same thing, you just take out the 1 and 0.
Okay, so you're going to say bin dot substring 0, like that. What's this going to give us? bin.substring 0 is going to give us literally the entire string. It's going to give us the whole thing. So we want really from 0 to bin.length minus 1. We want everything except the last character, right? And then we want to tack on what to the front. Oh, we want to tack on a closing parenthesis onto the front. Something like that. Move everything over by 1, so basically lose our very last far right bit and just throw an extra 0 onto the front of it. So that's a right shift. Okay. So if we were shifting this guy left twice, we would say test dot left shift test dot left shift, and we get our left shift twice. Okay. So now we might want to write a string multiply string bin by, we'll just keep it simple. We'll say int num. So we'll multiply it by a decimal number because we know we've converted stuff from decimal to binary plenty of times, so we don't need to deal with it. No, I lied. What's that guy called? What's this guy called?
I think, which thing is it? The asterisk thing?
No, the 5. These guys have names.
Oh, fuck, I don't know.
So like if this was division, this would be the divisor.
The numerator.
Is it the multiplicand? Is that right?
Ask Siri.
I don't even know how to ask it.
What are the thingamajiggers?
You guys have math classes. I mean, I haven't had math in 20 years. Is it the multiplicand? If this was 9 divided by 5,
Yeah.
that's the
There's
divisor.
The multiplicand and the multiplier. Yeah.
All right, so I got it right?
9 would be the multiplicand and 5 would be the multiplier.
Oh, 5 is the multiplier. Okay. See, you thought that was a made-up thing. Totally wasn't. Just I was using the wrong word. All right, so it's the multiplier. Okay. Now, funny thing is some of you guys didn't retain something from Tuesday. Last time I heard multiplicand was like before some of you were born. Anybody in here younger than 20? Just don't want to. Everybody in here is 20 or older? Oh. All right, so some of you were in diapers last time I heard that word. That's actually kind of sad. Now that I'm like kind of saying that I hear it out loud. Yeah, it's messed up. All right, so we're out of time anyways, right?
Yeah.
So at the beginning of next class, we want to write this guy. So we need to figure out what the largest power of 2 is that is less than multiplier. Make sense? And then we're going to do Amish's algorithm, where we're going to do the multiplication as far as we can go, and then let addition take us the rest of the way. Make sense? And in the end, we'll be left with something. Dr. Locklear is going to give you a slight curve on it when you take the senior seminar class. He's going to call it fast multiplication, but this is about 2/3 the way there. All right? I will see everybody on Tuesday. Remember, the homework assignment is up. You know plenty to go ahead and get started on it. There's only a couple of things that's on there that you don't know how to do yet. So you could probably finish 90% of it.
So I'll see you in like 20 minutes next to the hot tub.
All right.
We'll get to